This video will help review the material from Chapter 6 and Chapter 7 that will be appearing on your third exam. One thing to note is I did post some resources on our Google Classroom. I do have a set of notes that will help summarize the key formulas and ideas from the sections covered in the exam. And I'll also have this video as well as some other conceptual videos to help you better understand the material that's going to appear on the exam. So this is some of the information posted in my overview notes. So in Chapter 6 in Section 6.2, you were asked to find the probability or percentage of your data within your standard normal distribution that was either less than some stated value, greater than some stated value, or in between two values. So the procedure when you want to find that probability or percentage and you're given the data value to be either less than, greater than, or in between would be these three steps. So step one is you want to change the data value that you've been given into a z-score. If you're not quite sure what a z-score is, I will be posting a conceptual video to give you guys some help in terms of what a z-score is and why we use it. But the z-score here is essentially where our data value would be in our standard normal distribution. The standard normal distribution has a mean of 0 and a standard deviation of 1, and that's a very helpful distribution for us to be able to compare different data values and then also find our probabilities, since our z-scores allow us to find those probabilities in our z-score table. So how we would calculate our z-score is you take your data value, you're going to subtract the mean that you are given in the problem, so my data value minus the mean, and then I'm going to divide that result by my standard deviation. So here I wrote two forms. You may have seen this form with our sample mean x bar and sample standard deviation s, or our population mean mu and our population standard deviation sigma. So step one is convert your data value into a z-score. Step two is to look up that z-score in the table. So we would look up the row and column for the different decimal places of our z-score, and then on the interior of our table would be a number between 0 and 1. It's going to be some 4-digit decimal, and that 4-digit decimal represents the area underneath my curve starting from the left. So if my problem is asking for my probability or percentage that it is less than my stated value that we converted into our z-score, right? So if they said something like, what's the probability that all of your tested values are less than, say, 10, right? Where 10 is our data value that was given, then I don't have to do any adjustment to the value that I found in my table. That is automatically going to be the percentage or probability number that we want. If, in the problem though, they asked for the probability or percentage of data values greater than some stated value, then we do have to adjust our answer that we got from our table by finding the complement. So you would take 1 and you would subtract your percentage value that you found in your table to represent essentially this right-hand tail. So we know that our table always gives us the values to the left, so to find values to the right you have to subtract from 1. And then option 3 is the most complicated case. That may be where they are wanting to know the probability or amount of data values between two numbers, right? So if I ask for what is the percentage of values between 3 and 10 in my distribution, well then I have to go through that three-step process twice. I have to find the z-score for 10 and look up the probability from our z-score table. Then I would also have to find the z-score for 3 and then look that up in my z-score table. And then I'm going to subtract my values. So I'm going to take the larger percent value that we found minus the smaller percent value that we found in our table. And by doing that subtraction, we're going to find the piece in the middle of the distribution. So depending upon how your problem is set up, that will dictate which of the three options you go with at the end. So I picked some problems from your review that was posted by your professor so we can practice these. So number 12 from your review says the volume of soda in quart soda bottles is normally distributed with a mean of 32.3 ounces. and a standard deviation of 1.2 ounces. What is the probability that the volume of soda in a randomly selected bottle will be less than 32 ounces? So here I know that I'm going to be following that three-step process that we just mentioned, because the answer it's asking for is the probability, and the information that's given in the problem is a data value, in this case 32 ounces. So I want to know the probability that some selected bottle is going to be less than 32 ounces. So looking at my three options, we know that it's going to be this first option here, right? My data value being less than some given score. So step one, we need to convert our 32 into a z-score. So I'm going to use my formula. It's my data value minus the mean divided by the standard deviation. So I'm going to plug in 32 minus my mean, 32.3, and divide by my standard deviation, which is 1.2. Type that into my calculator, I get negative 0.25. So then from here, step two, I need to look that up in my z-score chart. So I have a negative z-score. So there's two pages here. So there's the positive z-scores, and then there's the negative z-scores. So I'm going to be looking at the negative z-scored side. I'm looking here for the row that has negative 0.2, and then I need 5. So here it's a little tricky the way that it's set up in the PDF, but if you notice the columns go 0, 1, 2, 3, 4, 5. So if I can't see those headings when I scroll down, I just count it out. So this is 0, 1, 2, 3, 4, 5. So this is my probability value that we were looking for. So 0.4013. That was from our table. And because I knew that this was case one, where I'm looking at the values that are less or to the left, which is how our table is already set up, I don't have to adjust this probability number to get my data values or my probability less than the 32. So this will be our final answer. Number 13, the lengths of human pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. And they want to know the probability that a pregnancy lasts at least 300 days. So here the word at least means we want our days to be greater than 300. So I'm looking at the data values that are going to be greater than a value of 300. So here, thinking of my three cases that we talked about, I am looking at the greater than case, which is option 2. So I'm going to be looking at option 2 this time. So I know once I find my percentage value or probability value from my z-score table, I'm going to have to find the complement. I'm going to have to do 1 minus that number to find the values that are greater than my stated cutoff. So let's first start step 1 by finding our z-score using our z-score formula. So here my value of interest is the 300. I'm going to subtract by my mean, 268, and divide by my standard deviation of 15. Now here when I type in my z-score into my calculator, I get a decimal that's 2.133333 repeating. But we only want to round our z-scores to 2 decimal places because that's the level of accuracy that our chart has. So I would round my number to 2 decimal places and then look up that value in our chart. So this time around my z-score is positive, so I'm going to use the positive sign. And I'm going to look for 2.1. I'm just going to put that at the bottom to make that easy. So 2.1 on my row, and then I'm going to look for 3 as my column. So I'm going to look at where those two intersect, and then I get the value 0.9834. Now, remembering back to our cases, to get my actual probability value, I need to subtract that from 1. So I'm going to do that now. And then that will actually get me the correct side. So if we think of our distribution or draw our distribution, we want the right-hand side. We want the values greater than 300. So to be able to do that, we need to subtract our value from 1 because our chart is always set up with values coming from the left. So the probability that I got here was 0.0166. Now, the other way that they could ask this problem is rather than asking for the probability or percent like we just saw, they could be asking for a particular data value given a probability or percentage. So those sort of questions would read something like, for what data value would 80% of your data be less than your value, right? So it's the same process, but in reverse. So we're first going to consider the 3 different setups. So they could ask for, the amount that is less than a particular percent, right? So 80% below, or values from the left. If that is the case, then we would just look up that value right up in our table, and we don't have to adjust for a situation at all. They could also ask for data values greater than a certain percentage, right? So in that case, again, we would use the complement. So I would be looking at, say, the 20% that's above my cutoff, just as an example. But I wouldn't look up 20% in my z-score chart because that's not the way that it's set up. So I actually have to do the complement. I would do 1 minus my 20%, and it would be that 80% that I actually look up in my chart. So we may have to adjust so that way we're getting always that value on the left. And then option 3, if they gave us the percentage in between 2 cutoffs, then we would have to look up each side of the cutoff based off of what information they gave us. So say they gave me the information in the middle was 60%. Well, I would have to account for this additional tail on the left-hand side. So if it's 60% and we know that it's centered around the mean, then I could say that there's 40% overall that's not included, with 20% coming from each tail. So in a case like that, when I look up my larger z-score value in my table, I would combine those. The 20% and the 60% means I'd be looking up 80% in my table, and then for the lower bound, I would just look up 20%. So we would have to adjust our case based off of the scenario that's being given in our problem. So once we've determined which case and what the percentages that we need to look up in the z-score chart, we'll use our chart again. This time we're going to use it a little bit differently. We're going to be looking at the interior of the chart for the probability value, and then looking at the column and row to create our z-score, right? So I would have like a z-score where maybe this was, say, 1.1, and this was a column heading of 0.08, and that would yield a z-score of 1.18. So we'd look at the row and column to actually find all the decimal places of our z-score. And then once we know the z-score, we're going to plug those into our equations to get back the data value. So you would take your z-score, multiply it by your standard deviation, and add your mean. So let's now look at some test review problems that relate to the topic that we just saw in terms of finding z-scores when given a particular percentage or probability. So here in question 3, they want us to find the z-score that is shown by our picture. So we can see that we have our normal distribution with the area shaded to the right. And they stated that that area was 0.8599. So here we do have to adjust our picture because we know that our z-score chart only gives us the area to the left. So this is kind of like that case 2 that we saw where we have to use the complement. So I need to go ahead and subtract off my 0.8599 from a value of 1. So the value that I am actually going to look up on my table is this area to the left. So the area to the left would be 0.1401. So to do that, I'm going to pull up my z-score chart. And this time we're looking at the interior of the chart. So we can see that the first page here with the positive z-scores, all my numbers are too large. They're greater than 0.5. And I want that 0.1401 number. So we're looking on the inside of our chart, trying to find the closest value. Oops. I want it highlighted. All right, so I'm looking for... All right, so here we were very fortunate. We were actually able to get an exact value. So here, this value right here, 0.1401, is the exact value that we were looking to find. If you weren't able to find anything that was exact, say it was in between two numbers, then you're going to essentially subtract the numbers that it's in between from the given number and see which one has a smaller difference. In other words, which one is closest in value to the value that you actually want. So here we were fortunate. It's actually exact. So if I look at my row, it's negative 1.0. And then I need to look up at my column. So it's the second column from the right, which we can see is 8. So looking at my row again, so 1.08 is going to be my z-score number. And that was negative. Problem 10 also has a similar setup, so let's look at this one. They want us to round to the nearest tenth. So a bank loan officer rates applicants for credit. The ratings are normally distributed with a mean of 200. And a standard deviation of 50. And they want to find P60, the score that separates the lower 60% and the top 40%. So here percentiles are essentially like our percentages in our z-scores. So they're looking for a cutoff value that's going to separate the lower 60% of my data from the upper 40% of the data. So here I'm really looking for that z-score that's going to create that 60% underneath my curve to the left. So we're going to start by looking that up in our z-score chart. So here I'm looking for 60%. We can see all these numbers are too low, so I need to go to the positive side. And this is a great example for where the area inside our chart doesn't quite fit. So here I can see my value of 0.6 is in between these two numbers. So I want to see which one is closest. So if I take 0.5987 and subtract that from 0.6, the difference is 0.0013. And then if I look at this other number, 0.6026, and subtract it, his difference is 0.0026. So the smaller difference between my desired value of 0.6 and the numbers we see here is this one, right? This one was 0.0013. So this is going to be the value that I pick to look up in the chart. So 0.25. So that is my z-score number. But here they're looking for the score. They don't want to know the z-score number. So in the previous example, they were asking for the z-score, so we were able to stop essentially at step 2 in our process. So if I go back to our process, if all you need is the z-score, then you can end here. But if you need to find the actual data value for your within your distribution, that's when you have to use your formula here. So for problem 10, we do have to go back and plug it into our formula. So my data value x is going to be my z-score times my standard deviation added by the mean. So let's plug that in. My z-score was 0.25. I'm going to have to clean this up. Give me 1 second. All right, that's much better. Okay, so 0.25, my z-score times the standard deviation. I'm going to add that by the mean of 200, and I get 212.5. And here, always look at what they want you to round it to. So they said to the nearest tenth, and here it is already rounded to the nearest tenth. So we're good to go there. Now looking at section 6.4, they introduced the central limit theorem. and how we can use that for sampling from a larger distribution. So here there are some given criteria we want to be aware of. So to use the central limit theorem, we need to make sure that our population or whatever distribution we're using does have a mean and a standard deviation known, and that the samples that we're going to be collecting from that distribution are simple random samples, right? In other words, I'm just randomly selecting different items from my distribution. I'm not just doing convenient sampling or some of those other sampling methods that we talked about earlier in the course. And we're going to do it of some standard size n. So I might be going in and doing samples of, say, size 10 every time. And we're going to be looking at the distribution of all those different samplings that we've done. So here, if I want to know the mean of all of my samples, we often represent it as mu with a little subscript of x bar. Should be the same as my population mean. If we do the standard deviation, though, we have to adjust for the fact that I'm doing multiple samples from my distribution, and that's going to affect our standard deviation. So the standard deviation for the mean of all those samples will be your population standard deviation divided by the square root of your sample size n. So when we do our z-score, then our standard deviation is going to be affected, right? So instead of doing my normal standard deviation, we would use that adjusted standard deviation. And one thing to note, from your course notes, you may have seen that the sample standard deviation is also sometimes called the standard error of the mean, or abbreviated SEM. Now that is for populations or samples that are greater than 30. If the original population is not normally distributed, and if the samples are small, in other words, the samples that I'm gathering from that larger population are less than or equal to 30, then that means that this method can't be really used, that it's not going to be a good approximation of the mean and standard deviation. So keep that in mind, that we do want our sample size to be greater than 30 to use this distribution of the sample means. So looking at an example of that is problem number 14 from our review, and it says the annual precipitation amounts in a certain mountain range are normally distributed, so that fits one of our requirements. We know the mean of the distribution is 109, and the standard deviation is 10. What is the probability that the mean annual precipitation during 25 randomly selected years will be less than 111.8 inches? So here what tips it off that it's going to be this distribution of the sample means is they're doing 25 randomly picked years. So here, because they told me that my distribution was normal, we know that we can use this method, even though I'm only doing samples of 25. So I know that I'm going to be doing sample sizes of 25, and we want to know the likelihood that any of those particular samples are going to be less than the 111.8. So in many ways this works just like what we saw as our first set of problems in the review. We're going to calculate our z-score and then look that up in our table and then use that table value for our answer for the probability. But the key difference here is that now that I'm doing these samples, that's going to affect what I use as my standard deviation and what I use for my z-score formula. So we know that the mean for our samples should be the same as the mean of our distribution. It's the 109. The standard deviation, though, we know is going to be adjusted because of our sample size. So I'm going to use the standard deviation of my population and divide by the square root of my sample size, my n. So here that's going to be 10 divided by the square root of 25. So that's 10 divided by 5, which the math isn't too hard, that's just 2. So when we calculate our z-score, we're also going to have that adjusted formula. Now here, because I did adjust my sample standard deviation, you could use your z-score formula kind of like we have in the past, just knowing that we're using the mean of our standard deviation, the mean of our samples and the standard deviation of our samples. So plugging it in here, my data value is the 111.8. minus my mean, 109, and our adjusted standard deviation of 2. So that gives me a z-score of 1.4 that we can now look up in our table. So I'm going to look up 1.4, and then there's no hundredths place, so we can just consider that 0. So it'd be this number here, the 0.9192. Now here we would want to consider whether we have to adjust that number based off of how they set up the question. So here they want the values less than 111.8. So they're looking at the values to the left of the z-score that we found. And that's how our table is naturally set up. So in this case, I don't have to adjust our probability at all. So that 91.92% would be our final answer.